Welcome to our second lecture on our lecture series on design and detailing of structural steel connections. This is our second lecture. In our previous lecture, which was an introductory one, we discussed why it is important to learn design and detailing of structural steel connections. We discussed 2 or 3 reasons as to why it is important. And from today we will be starting with the discussion of connectors. So as we discussed in our previous session, connectors means there are 3 or 4 different types of connectors is indicated in our IS code, but we will study only the 2 most important one. We will start with bolts today, and in our upcoming lectures we will discuss about welds. So if we talk about the Indian code dealing with design of steel structures, it is IS 800 2007, and in this IS code the section 10 of this IS code deals with the design of connections in general. So let's say this section 10 deals with the design and detailing requirements for joints between members. So this is what is written in the introduction to section 10 in this IS 800 code. So section 10 deals with the design and detailing requirements for joints between members, and it also says, as we discussed in our first lecture, the connections in a structure shall be designed so as to be consistent with the assumptions made in the analysis of the structure. We discussed how our design should be consistent or should conform with the design or analysis assumptions by discussing 2 cases in our previous lecture, in which we looked at the bending moment diagram of a beam in which the joints were assumed to be rigid, and the bending moment diagram for the same beam in which we had applied releases so that there was no moment transfer. And we discussed why it was important to design the connections so that they conform to the assumptions made during the analysis of our structure. So this was the recap of our previous lecture. Today we will start with bolts and action on bolts. So first let's look at what are bolts. Bolts are, as we said, bolt is a connector such that it has head at one of its end. This part of the bolt is known as head, and this part of the bolt is known as shank. So bolt is a connector which is composed of 2 parts, head and the shank. You can see that the shank is threaded at the bottom portion. This length L of the bolt is threaded, and you can see that the head is of a hexagonal shape in this diagram. This may also be of a shape of a square, but the hexagonal shape head is the most commonly used in practice because it is aesthetically also it looks pleasing, and also because of the hexagonal shape of the head, it is easy to turn the bolt with the help of wrenches in the case of this hexagonal head. So the bolt is a connector which is divided into 2 parts, head and shank. The bottom of the shank is threaded. This is the threaded portion of the bolt, and usually what we do is, in this threaded portion there will be another part that will be used while clamping the structure with this bolt, and it is known as nut. And below this head and also above this nut, generally we use washer. Washer is some kind of plastic material that is used for clamping any 2 parts with the help of this bolt. And what is the function of this washer? The function of this washer is to properly distribute the clamping forces that we apply using wrenches or any other material. So this is the general definition of a bolt. This is the head, this is the shank, and we use a nut at the threaded portion. So when it comes to bolt, we have to deal with 2 main characteristics or property of bolt. One is the diameter and another is the grade of bolt. So let's first discuss what is the diameter of the bolt. Diameter of a bolt is the diameter that is measured at the shank of the bolt. Suppose that this is the head of the bolt and this is the shank, and we have the threaded portion here. So the diameter of the bolt is the diameter that is measured at the shank, and this, let us say, is represented as D here. The diameter of the bolt may vary in values, and generally the diameter starts with some value of 5 mm or even 8 mm, and this diameter may even reach up to 32 mm. So different sizes of bolt are found in use, and the diameter is generally represented by a letter M, and after M we generally put the number that represents the diameter. For example, a M12 bolt means it is a bolt of 12 mm diameter. Similarly, M20 bolt is a bolt of diameter 20 mm. So this is about the diameter of the bolt, and second is the grade of the bolt. So what is the grade of the bolt? The grade of the bolt is generally represented by such numbers as 4.6, 6.6, 8.8, 10.9 and something like this. So the grade of the bolt represents the stress or the strength of the bolt. This 4.6 is generally known as a mild steel bolt. We will see why it is called mild steel bolt. And the remaining grades, these are generally referred to as high strength bolts. So why is this called mild steel bolt? To know this, we have to first understand what these numbers that are representing the grade of bolt means. For example, let us take this value of 4.6. So these two numbers have different values here. So what does this first number 4 represent? This number represents the 1/100th of the ultimate stress of material of bolt. Ultimate stress of material of bolt, that is Fu in Newton per square millimeter. So what does this mean? 1/100th of ultimate stress of material. That means to determine this ultimate stress, what we have to do is we have to multiply this 4 with 100. So the ultimate stress of 4.6 grade bolt is 400 Newton per millimeter square. Similarly, what does this number after the decimal represent? 0.6 or 0.6. This is the ratio of the yield stress of material, that is Fy, and the ultimate stress of material that we calculated here, Fu. So if we want to calculate the yield stress of material, what we have to do is we have to multiply this Fu with the value 0.6. Fu we have obtained is 400 here, 400 into 0.6, this is 240 Newton per mm square. Now you can see why this 4.6 grade bolt is called mild steel bolt, because the yield stress of this material is the yield stress of a mild steel, 240 Newton per millimeter square. So 4.6 grade of bolt is the mild steel bolt. Similarly, you can calculate this Fu and Fy for other bolts also. For example, if you take this 8.8 grade bolt, the ultimate stress of material is this first 8 into 100, which is 800 Newton per millimeter square, and the yield stress is 0.8 into 800. This comes out to be 640 Newton per millimeter square. So in this way, these are the different grades of bolt, and we looked at what each number in this bolt represents. So 4.6 grade bolt is a mild steel bolt, the remaining are high strength bolts. Generally, we use high strength bolts for the design of different structural steel connections. However, In one particular case, we tend to use this mild steel bolt, and that is generally during the design of column base plate connection. So why do you generally prefer mild steel bolt for the design of column base plate connection? We will see that when we discuss the design of column base plate connection. So this is about the two properties of bolt that I intend to discuss. First is the diameter and another is the grade of bolt. So here I have posted a screenshot of clearance for fastener holes, the table 19, which I derived from the same IS 800 code. This table gives us the size of the hole pertaining to the diameter of the fastener. For example, we know that to clamp any two plates with the help of bolts, we first have to make a hole in them. If you look at the plan view, for example, we have to make a hole here, and in this hole then only we can insert the bolt to clamp these two plates together. So what is the diameter of the hole that is generally taken? This depends on the diameter of the fastener, or let us say the diameter of the bolt. So what this table gives us is, if the diameter of our bolts ranges between 12 to 14 mm, the standard clearance is taken as 1 mm. That means, for example, if we have a 12 mm dia bolt, the size of the hole for this 12 mm dia bolt will be 12 plus 1, that is 13 mm. Similarly, for diameter between 16 and 22, we take 2 mm. For example, if we have a 20 mm dia bolt, the diameter of hole for this 20 mm dia bolt is 22 mm. Similarly, for 24, we use the same value of 2, and larger than 24, we use the value of 3 mm. So this is the general discussion for clearance for fastener holes based on IS 800 code. And when do we need this? When do we need to calculate the diameter of holes used for bolt? We generally use this when we are calculating the capacity of a bolt. So we will look at the capacity of calculation of this bolt capacity maybe in our next lecture or the lecture after that. We will need to use this value of diameter of holes when we are calculating the capacity of bolt. So after discussing about these two general properties and the most important properties of bolt, because these are the properties that we need to determine or that we need to fix, that we need to consider when designing for any bolted connection in the case of bolts. So after discussing this, now let us come to one very important part. What are the actions on bolts? Action on bolt means what are the forces that may come onto the bolts. Actions on bolts. So there are three major actions that will come into a bolt. One is the bearing action, another is the shearing action, and another is the tension force on the bolts. So these are the three main actions that come on the bolt. So to discuss about bearing and shearing, first let us look at this diagram here. You can see that in the first diagram, the two plates are being clamped together by a bolt of diameter D, and each of these plates is being pulled by a tension force P in one direction for the upper plate and P in another direction for the lower plate. Similarly, for the second diagram, you can see there are three plates being clamped by one bolt. The middle plate here is being pulled by a force of P, and the other two plates, the first plate and the third plate, are being pulled in the other direction by P by 2 and P by 2, such that the total force is in this direction is again P. So let us consider first this single shear joint. We will see what is single shear joint. Let us consider this first diagram here. Let me make the diagram. So this is the first diagram here, and suppose that, okay, let me draw it solid line for now, although it may not be visible. So this is our first diagram. So what happens here is, as you can visualize, when the upper plate is being pulled in this direction by a value of force equal to P, we can say that this plane here, that means the plane where the bolt is in contact with the plate here, this plane will be acting or will be acted upon by some bearing force. And where will that bearing force come from? The bearing force will come from the plate bearing on this bolt here. For simple understanding, just remember that bearing in simple sense means it is supporting on or being supported by, so that those two planes are touching each other. So if I just draw this bolt here, because this part of the bolt is bearing on the plate, or let us say that the plate is bearing on this bolt, this plane will be here acted upon by some bearing force. Let me draw it in this way. The plate is acting some force, or the plate is causing some force to be acted upon this bolt here, and this is the bearing force. Similarly, if we look at the plate below here, this is being pulled in the other direction again with a force P, and as for the above plate, now this part of the bolt will be in contact with the plate, and again the plate will have some bearing force being exerted on this bolt, so that now the force is acting on this part of the bolt in this way. So this is also a bearing force, and this is also a bearing force. And another force that will be acting here is, if you look at this middle plane here, let me draw it with another diagram. Okay, if you look at this plane here, now you can see that some shear is acting in this plane here. Why is it so? Because if you pull this bolt in this direction with some force, and again in this direction with some force, you can assume, or you can sense, or you can also visualize that some sort of shear force will be acting here, because these two parts are being pulled in the opposite direction. Similar to what we do for a beam here, let us say if we cut the beam at some place, we can say that some force is acting downward in this side and upward in this side. This is the shear force acting on our beam. Similarly for the bolt, since these two forces are being acted in two directions, there will be a shearing plane here. There will be a shearing plane here. So for this diagram, if you see, we have two bearing forces. We have two bearing forces and one shearing plane. And one shearing plane. So because there is only one shear plane here, we call this as single shear joint. Since only one shear plane is present here, we call this single shear joint. So this is what is meant by single shear joint. And please remember that now we are not concerned with whether the bearing force or the shearing plane lies in that part of the bolt where there are threads or not. We are not concerned with the threads for now. We are only discussing about the types of action that may come onto a bolt. It will make matter, or it matters whether that force is acting on that part of the bolt where there is thread or not, but that will only be discussed when you are dealing with the calculation of bolt capacity. Now we are not concerned with that. Now similarly, let us look at this second figure here. Now I am not going to draw a different figure for now, because we have already understood this here. For this second figure, now similar to the first figure, because this first plate and this third plate are being pulled in this left direction by a force P by 2, this part of the bolt and this part of the bolt, there will be bearing forces exerted by this plate here. Because this plate is being pushed in this direction, the plate will bear upon the bolt. Similarly, in the case of second plate here, the plate is being pulled towards this right hand side, so there will be bearing on this surface. And as we discussed in our first case here, one plane here and another plane here, there will be shearing forces, or this is the shearing plane. So now we can see that in this case, there are 3 bearing surfaces and 2 shear planes. Because there are 2 shear planes, this is known as a double shear joint. I hope you have understood this, why it is called a single shear joint and why it is called a double shear joint. You should be able to visualize this, because when we are calculating bolt capacity, we need to consider whether there is single shear joint or double shear joint. So that we have discussed 2 forces or 2 actions on bolts, bearing and shearing. Now if we look at this third diagram here, for every diagram I have mentioned the image source from the internet or the internet website from which I have taken this diagram here. If you look at this diagram below here, you can see that these 2 plates, one plate here and the other plate here, these are being joined or clamped by 2 bolts. One bolt is here and another bolt is here. So if we pull apart these plates using some value of force in 2 opposite directions, then what will be the type of force that will be exerted on this bolt? As you can see, as these plates are pulled apart, the same type of force will be transferred to these bolts also. These bolts will also be pulled apart in this way. So what are these forces that are acting on these bolts? These are the tension bolt. A simple bar, if you pull in opposite directions in this way, you know that this is known as the tension force. So because of our forces acting on this plate combination here, the bolts are also being acted by tension force. So these are the 3 actions of bolts that is important and that we need to discuss while calculating the bolt capacity also. So remember, just notice one thing here. You can see that in this first diagram that we discussed, there are 2 diagrams, and in each diagram you saw that even in this first case also there was both bearing surfaces and shearing plane, and also in this second figure also there were both bearing surfaces and shearing planes. So what we have to say is that these 2 actions, bearing and shearing, they always occur in pair. That means if there is bearing forces on a bolt, then there should be shearing forces also, or if there is shearing forces on a bolt, there should be bearing also. One cannot exist without the other. So bearing in absence of shearing is also not possible, and shearing in absence of bearing is also not possible. However, if you look at this diagram here, you can see that the tension force can exist independently. So tension force is not associated with bearing or shearing, it can exist even independently, but where there is bearing there should be shearing, and where there is shearing there should be bearing forces. So after knowing this much, you can see that the 3 primary actions on bolts are bearing, shearing and tension, and when we are calculating the bolt capacity, we have to consider all these 3 actions on bolt. Bearing and shearing always occur together, whereas tension is independent of bearing and shearing. So what we discussed today in our first lecture, after our introductory lecture, we discussed first about what is a bolt. We looked at a simple diagram of a bolt. We discussed about its diameter and grade, and we discussed the important thing, these are actions on bolt. We looked at bearing, shearing and tension forces. So this is the end of our lecture on bolts and action of bolts. In our next lecture, we will first look at some member forces or forces in the connection, how those forces get transferred in different types of connections, just for some visualizations, and then we will go to the capacity calculation of bolt. So before ending our today's lecture, let me just say one thing. You may already know this also, in design of steel structures, we already discussed in our first lecture that connections are probably the most important part. So in our design of steel structures, which do we design first? Do we design the members, that is beam, column, etc.? Do we design the members first or do we design the connections first? So you think about this question. When we begin our next lecture, we will first discuss with the answer to this question, and then we will go to the topics for our next lecture. So this is the end of our lecture for today. Thank you, and keep watching videos on our YouTube channel.